Good morning. We are going to deal with voltage control and reactive power support. That means in ancillary service management in a restructured power system. So why this voltage control is needed in power system? If you see like voltage magnitude is mainly controlled by this reactive powers. That means VAR. Unit of reactive power is voltage amperes active power, that means the power generated from the generator, that means megawatt, controls the frequency, but the reactive power MVAR controls the voltage. If voltage is not controlled properly, insulation stress increases in the transmission tower, and as well as motor overheats. Next, power electronic devices fails. Next, and also not only insulation stress of the particular equipment, whatever the equipment connected is, will be increases. Next, the system may experience voltage instability or collapse. What are the main key differences from the frequency control with respect to the voltage control? So if you take like control quantity, frequency control, the control quantity is frequency, hertz, voltage control, the control quantity is obviously voltage, that means kilovolt per unit. Next, the power involved is active power in the frequency control. The power involved in the voltage control is reactive power, that means MVAR. So what is the nature of frequency control is global control, and voltage control is local control. Next, propagation. Frequency control travels a long distance, but voltage control is a poor long distance transfer. Okay. Next, control objective. Load generation balance. Okay, load generation balance. Here, the voltage control, voltage stability. Okay, here it is automatic generation control. Here it is AVR, voltage control, automatic voltage regulator control or voltage regulation. So next, frequency is a system-wide issue, but the voltage is a local issue. Frequency is whole system, but the voltage is a local issue in that particular distribution station like that. Distribution system like that is a local issue, but frequency is a system-wide issue. Frequency spoils, then whole system get collapse. But if the voltage spoils means here the reactive power, okay, reactive power, that control we need to do here. Next, why reactive power is a local service? So reactive power does not travel well over long transmission line because it causes a high I square R X losses. That means I square R reactive reactance losses. So it consumes transmission capacity. Okay. Also, voltage drop increases rapidly with the distance. Therefore, reactive power must be produced close to the load. Okay, so reactive power must be produced close to the load, whereas voltage control is a location specific. That means nodal. In that particular node, it is the location specific. Voltage control is a location specific. Next comes the definition for voltage control and reactive power support. So voltage control and reactive power support is an ancillary service in which independent system operator or transmission system operator injects or absorbs the reactive power to maintain the bus voltages within the permissible limits. So what is the typical voltage limits means plus or minus 5% of the nominal voltage. So if you take in per unit, it is 0.95 per unit to 1.05 per unit in terms of per unit. Because in power system, all we are dealing with the calculations, we are dealing with the per unit. So what are the main objectives of this voltage control services in the sense? It maintains the voltage profile. That means keeps the voltage within the saturatory limits and also ensures the reliable operation of the equipment. Okay. Next, prevents the voltage collapse. That means ensures the sufficient reactive reserves and supports the system during the contingencies. That means transmission line or generator. outages in that particular system. It supports the support system during the contingencies, and also ensures that sufficient reactive reserves are available. For example, heavy loading, okay, plus insufficient wear support. For example, heavy loading is there, heavy load demand is increasing, so load is heavy, and insufficient reactive power support is there. Next, progressively voltage drops may occur, so which collapse the system. So improves the power quality. How to improve the power quality? So over voltage, if you see over voltage, insulation damages will be occurring. Say for example, that equipment will be designed for particular voltage only. If over voltage occurs, automatically insulation. If you say, for example, wires in our homes, so even though tolerance limit will be there for wires, but insulation damages will be happening. Next, under voltage, motor stalling effect will occur. Okay, so next, that means motors runs at very low speed. Okay, next, and it will spoil. It also spoil the lifetime of the windings. Next, voltage fluctuations. So due to the voltage fluctuation, what happens? Flickering effect. Okay, the you can see in the incandescent lamp and in old tube lights, this kind of flickers. Sudden drop in the voltage, automatically that tube light will flicker. Like that. Okay, which minimize the system losses. Okay, minimize the system loss. So proper wear management, that is reactive power management, reduces the IR square losses and as well as the IR square X losses. So and also improves the transmission efficiency. In turn, improves the transmission efficiency. That reactive power, if you improve, automatically transmission efficiency get improves, increases. So relieves the transmission congestions. So which reduces the reactive power flow on the lines, and also free line capacity for the active power transfer. Okay, so reactive power control indirectly increases the megawatt transfer capability. Okay, reactive power control indirectly increases the you need to generate more if the reactive power control is not there. So reactive power control, because if reactive power is indirectly increases the megawatt transfer capability. Okay, so that is also one of the indirectly increase, that is because reactive power should be there to increase the power transfer capability. Okay, then only this point is very very important. Okay, reactive power indirectly increases the power transfer capability. Next, levels of voltage control. So voltage control is implemented to three-level hierarchy, like frequency control. First is a primary voltage control. Same thing we have seen, no, primary frequency control, secondary frequency control, tertiary. So same here also, primary voltage control is there. That is fast, automatic, and local control. That means it acts within milliseconds to seconds. So implemented via this AVR. That means automatic voltage regulator. So what is the feature? Feature in here is based on speed. Primary control is very fast. Control local. Device automatic voltage regulator. What is the objective? To arrest the voltage deviation. Secondary voltage control. So here coordinated control over a region, maintains the voltage profile across the multiple buses, managed by the independent system operator and transmission system operator control center. So this is called secondary voltage control. Okay, speed, if you take the speed within the seconds to minutes, secondary voltage control within the seconds to minutes. Control is centralized. What is the objective? To restore the desired voltage profile in the power system or in the transmission lines. Next comes the territory voltage control. So territory voltage control, long-term economic optimization is there. Placement and scheduling of where resources we need to plan. Okay, so where to place the your reactive power control devices and the scheduling of where resources. That and all you should plan. Next, typically manual or market-based control will be there. So if you take like speed, Minutes to hours. Tertiary control means minutes to hours. Control means market or manual control should be there. Objective economic where allocation should be there. Okay, so minutes to hours. Okay, not immediately, some hours. So control means market or manual based control. Objective is to economic where allocation. Okay, so wherever this reactive power is, economically we need to plan. Then only cost of this reactive power control devices should be decreased. Next, sources of reactive power supply. Say, for example, synchronous generator. Okay, more flexible traditional sources. So provides the wear compensation by adjusting the excitation. Okay, over excitation and sometimes under excitation. So controlled via the AVRs, automatic voltage regulators. So what main issue is here? Opportunity cost issue. To supply more reactive power, let me say VAR, the generator may needs to reduce the megawatt output. So if the megawatt output reduces, automatically the reactive, but we need to balance the load also. That thing also we need to take into account. Okay, so response speed, if you take like a fast generators, speed is fast, control range is wide for the generators. Cost, if you take like opportunity cost. Okay, so based on to supply more reactive power, the generator may reduce this megawatt power output. Then only reactive power flow will be. That is also you need to take it into account. Next, the limitation. What is the main limitation? Megawatt MVR trade-offs. That also is there in the generators. Or in restructured power system, that controlled within the generator companies, generation companies. Next, we need to use the passive device like a shunt capacitor. Okay, supplies the reactive power and improves the voltage during the heavy load. Okay, so if you take like action, voltage increase action. If you take like shunt capacitance, voltage increase. Why we need to insert the shunt capacitor to increase the voltage immediately. Next, that shunt capacitor might be of switched control. Switched control also possible because sometimes increase, sometimes decrease. So switched capacitance. Okay, switched shunt capacitance. So if you take like a shunt capacitor, cost is low. Okay, what are the limitations? You need to increase in discrete steps. Some monitoring devices should be there, and decrease the discrete steps only you can increase. That is one of the limitation. Coming to the shunt reactors. So shunt reactors means inductance. So it absorbs the reactive power and also used at the light load as well as the Ferranti effect also will induce in this shunt reactors. If you take like a voltage reduction shunt reactors, what is the main role of the shunt reactors is voltage reduction. Okay, sudden if the voltage increases, suddenly you can put the reactors inside and suddenly voltage get reduced. And if you take like a usage for light loads, only for light loads, cost is moderate. So, but if you take like system like India, reactors usage is very less places we are using because load demand is rising and generation also equalizing. So whereas this reactor usage is very less. If you take like some foreign countries might be there, might be using, but in India, this reactive control is very less usage and cost also moderate. Next comes the active compensators. That means fax devices. So modern, this fax devices are modern and power electronic based devices. If you take like static wire compensator, okay. So here thyristor controlled capacitors are there, and as well as reactors. So which type is based on say it will always detect this one compensation. So whenever the voltage reduces based on the thyristor control devices, automatically reactor will comes into the picture and automatically this compensation happens. So continuous controls. So if you take like STATCOMs, more advanced voltage ampere reactive source will be there. So response, if you take like in STATCOM, if you use static compensator, it is based on the subcycle, and also performance at the low voltage is excellent. Okay, control is continuous, cost is high. This static compensator. Okay, so if you take like regulating transformers, uh, like on-load tap changing transformers also there. So sudden change in the load, so automatically this transformer will react. Okay, tap changing transformers, voltages to increase or decrease. Okay, so if you, depends on the winding. Suddenly rise in the voltage happens means you need to increase the winding. So suddenly voltage get adjusted. So adjust the voltage by changing the turns ratio. That means wind turns ratio of the transformer. So if you take like a feature, this OLTCs are on-load tap changing transformers are slow and the control is discrete. Usage is distribution and transmission. We are using this OLTC transformers. So if you take like comparison of the reactive power sources, generators, sources in terms of generators, capacitor, reactors, SVC, STATCOMs, and OLTC. Speed, if you take a generator fast, control is continuous, cost is based on the opportunity cost, the usage is dynamic support. Capacitor, speed is low, control is discrete, cost is low. Next, usage is for steady low. Okay, steady load. Next, capacitors are mostly used. Next, reactors. Speed is slow, control is discrete, cost is moderate, and best used for light load. But this kind of light load maybe happens in very few times. Okay, so based on that, our generation itself will decrease based on the feedback. Next, if you take like static wire compensator, speed is fast, control is continuous, cost is high, and usage is for transmission lines. Next comes the STATCOMs. Speed is very fast, control is continuous, cost is very high, usage is for weak grids. Okay, next comes the OLTC, on-load tap changing transformers. Speed is slow, control is discrete, cost is moderate, and usage is for voltage leveling. So if you take like a economic management in a restructured system, unbundling of this reactive power services should be happened. So where support is separated from the energy market, okay, and also where support is separate entity. This ancillary services is separate entity. Okay, next paid as a ancillary services. This where support and all. Okay, that means unbundling of the reactive power services. Okay, so we are taking out this reactive power service and making it as separate entity. Like so, next is market based procurement. ISOs used nodal pricing methods. Next, zonal where markets are there. Okay, next, forward or auctions for reactive capacity. This is also there. Next, reactive power prices depends on the location, not just on quantity. Okay, depends on the location, not just on the quantity. Okay, so ISOs use nodal pricing. Nodal pricing means based on the particular nodes, based on some areas, the pricing will be happening because where that means where support, reactive power support might be different. So because if you take in the entire system, then it is very difficult to collect. So whichever node is they are utilizing more, they will be charged. And as well as nodal, zonal wire markets based on the particular zones where the reactive power compensation are happening. There they are costing more on that. That means that charge also, tariff also, you need to pay to retailers or this transmission companies. Next, forward auctions. Auctions, how to make it for reactive, like auctions might be made. So which reactive power support utility will be taking care of which zone, like that, based on the auctions they are deciding. Next, reactive power prices depends on the location, not just on the quantity. Okay, based on the location and nodal, that means nodal and zonal areas. So if you say take like a compensation component, availability, that means capability to supply and absorb the reactive power. Next, if you take like losses, extra heating losses and losses that in the transmission line will be there. Next, opportunity cost, low megawatt revenue generator will be chosen. Okay, so next is performance, speed and accurate will be there. Next, renewable integration, reactive power supports. So if you take like smart inverters, uh, wind and solar plants must provide where support will be there. So enabled by the advanced inverter controls. Nowadays, due to the more advancement, the smart inverters, its name itself smart. Okay, automatically it will be compensating the reactive. It will be providing the reactive support in that particular areas by with the respect to wind and solar plants and also as well as advanced controls. Next, Federal Electricity Regulatory Commission, Order number 827 and its updates clearly given mandatorily reactive capability should be there. Okay. Next, paid as an ancillary service. This reactive power support also will be paid as an ancillary service. If you take like where capability in renewable system, it is there. Yes. And if you take like control, based on the inverter based control, revenue share up to approximately 11%. Benefits, voltage support at the distribution level. Next comes the voltage control versus the frequency control. So if you take like an aspect like a controlled power, voltage for in the voltage control, MVR control is there. Okay, that is reactive power control is there. Whereas in the frequency control, megawatt control, that is power active power control is there. Okay, here reactive power, here active power. Okay, voltage control means reactive power. Next, nature is a local control, and as well as here nature is global control. Overall it has to control overall frequency, but voltage control, you need to control in that specific areas, based on the nodes or based on the zone, that particular zone, like that. Main devices, if you take like AVR, automatic voltage regulators, okay, and fax devices, capacitors are used for voltage control. If you take like a frequency control, governors, AGCs are with respect to automatic generation controls, and as well as some governors will be governing this frequency control. Here, market design based on the nodal voltage control. If you take based on the nodal analysis, frequency control, system wide control will be there. So failure risk, if you take like voltage control, voltage collapse will be there. For frequency control, system blockouts. Okay, so voltage collapse, failure risk means if voltage is not maintained, so voltage collapse in the system. But if the frequency you are not maintaining, which sometimes the system blockout, the system will be fully uh, go away, because the frequency is very important factor in the system. This is the comparison between the voltage control and the frequency control in the restructured power market.